Okay, well, we didn't end up having a dot cam in here, so we're going to have to kind of do some things a little weird here. What we're going to do is basically dive into the first problem here. I put up what we talked about a little bit on Tuesday, the two trigonometry functions that we're going to be using through a little bit of the class here, the law of sines and the law of cosines. Now, one thing to note, then, just in terms of what you can do with those equations, is with the law of sines, if you have two magnitudes, an A or a B or a C, and one angle, well, with that information, you can solve for an unknown angle. And vice versa, if you have two angles and one magnitude, basically, you can solve for one magnitude. So you think about in terms of what knowns and unknowns you have. And then finally, law of cosines basically says I need one angle, but I need definitely two magnitudes there. So in order to use those, you need to think about, OK, what do I have in terms of what's known and unknown? So we're going to start off with problem 2-3. And you've got your little quad paper there, basically, you can work on. So when you're, as engineers, we generally like you to work on the quad paper because you are going to be doing a lot of drawing. Ma'am? Should have been a whole bunch of extras. Are there any in the back floating around? Oh. Can we pass those over here to... Okay, so what we're going to be doing now is just exploring how we're going to be dealing with forces, how we're going to combine them, how we're going to break them up into pieces and stuff. Basically, how to add them together is going to be the key thing. Now, what we've got is a couple of forces there, a P and a Q. They've been given values. We have angles measured from some coordinate system. And what we're going to be doing then is just playing around with different ways of getting to the resultant. What we're interested in is the resultant. You know, how much force is going to be putting on those bolts and that sort of thing. We can look at the individual forces, and in that case of the gusset plate there, we can look at the forces of the bolts on each of those forces. But if we want to look at the whole bracket, we're going to be interested in how the whole bracket is responding to that. So in terms of a graphical approach, what this does is just gives us a clue. It's not super accurate, but it gives us an idea. One of the key things we want to think about when we're solving problems is, have we reached a reasonable answer? You know, is it 10 to the million, you know, and then one force was 10 and the other one was 12? Then we need to start thinking. So part of being an engineer is it's not just simply plugging and chugging and coming up with answers there, but thinking about the reasonableness of your answer. Does this make sense? Now, one of the ways you can do that is graphically. Basically, you can, that's why we use the graph paper. Fortunately, I'm going to have to try it on the board here because I can't show it on a dot cam. But what we'll be doing is setting up a coordinate system. So we'll have a, that's a minus x actually, because the forces are going that way, and of course everything going to the left is negative. Now, one of the things we'll be doing is in terms of a graphical approach, we're going to set up things to a scale. Now, on your graph paper there, each of those squares is a 1/4 inch square, okay? So what we can do is get our little rulers out, basically, and we're going to say each newton is going to be equal to 1/4. So when we look at P, P is what? Okay, so that will be, in terms of the scale we're going to draw that, it'll be 10 times of those quarters, or 10 over 4, or 2.5 inches. Q will now be, what is that, 15 over 4. And that length will be 3 3/4. So when we draw it graphically, what we're going to do is pay attention to the fact that our magnitudes now, as we talked about, are going to be lengths.
Would it be 1/4 equal to 1 kilonewton?
Would 1/4 what? 1/4 equals 1? Oh, is a kilonewton? Oh, yeah, you're right. Thank you. Yes. Somebody's had their coffee today. Okay, so then when we draw that, what we're going to have to do is then we'll pick a point. Notice that those 2 points intersect, or those 2 forces intersect at a point there. What we're going to do, and this is where I would have my scale out and everything else, but unfortunately we can't do that. What we'll do with our protractor is basically come up with so we'll take our protractor basically and go out there to measure 50 degrees down from here, and then 25 degrees up there. Draw our lines in, and then we're going to put in terms of kilonewtons, as the young gentleman pointed out there. So we're going to measure that out as 2.5 inches. And we'll do the same thing with the Q. Like so. Then unfortunately, the cool trick I wanted to show you is how you can set your protractor in a triangle and slide it. But basically what we're going to do then is take that same, we're going to draw a parallel line to that and a parallel line to that from the tips. And what we'll find then is this is the point where our 2 forces will intersect. And this will be the, well, let's make sure we get some other things up here too. So same thing here. This is 50 degrees. And via the parallelogram law, notice that it looks like a parallelogram. What we're saying then is that our resultant basically will be that. And then if you actually had your rulers and that sort of thing, you would go and measure that. And when we measure it, we see R is around 5 inches, which then we can convert via our scaling there. So it should be around 20 kilonewtons. And then I can measure this angle. And we measure it from some convenient location in terms of this particular one, the x-axis there. So again, this is not going to be the super accurate answer, but when you start plugging and chugging, if you come up with 500 or something like that, you'll know something's wrong. This is an idea of simply giving yourself some thought as to whether this is a reasonable answer. And this is why we use graphing paper. Now this is the graphical approach, so this will be something you'll be doing, and again, this will be one of those things that you'll draw, put in your notebook so I can take a look at it and that sort of thing, because you're not going to be able to come up with an answer unless you do it on the graphical approach. And then basically the computer or the website will have you go ahead and plug in the numbers and that sort of thing. So that's the graphical approach, part A. The other approach is the triangle. And again, note that when we look at this parallelogram, we'll see a triangle on either side. It's a very similar approach. This one's nice because basically you do both of your angles from the same point and then just simply draw the parallelogram. If you want to use the triangular approach, it's just simply what you do is tip to tail construction. So what we're going to do then is put in, so it's the same scale. So we'll put the first one in, and then what we do instead of drawing the line there, we're going to take our protractor, bring it down here to the tip of this. And we're going to move our protractor down here, basically. Set up the tricky thing about this is whether you can find a nice line to bear it up against there. But basically what we're going to do is then, make sure I don't do it too far. And then we're going to, at the tip of that arrow then, substitute in now or add this P, which will be at 25 degrees from the horizontal there. And then it's going to be the 2.5 inches. But again, it gives us the same result, basically. Our resultant is just simply this half of the triangle. And as you can see, it doesn't matter whether I do this side or whether I choose this side. Basically, both of them will get me there to the same point. Okay, so this is the approach in terms of simply drawing it out. And again, the reason why you draw things out is as engineers, you're always going to be checking your numbers. Am I reasonable? Am I close? What should I expect to see out of that? Now, there's another approach where we're going to be taking advantage of the equations there, sines and cosines. And what we want to do is take one of these triangles here, and I'm going to draw it a little bit bigger here. And we're going to want to find that R and find that angle. So a couple of things. We can use what we call the force triangle. We've got this triangle here. What we're going to do is basically look for those internal angles and then simply apply one of the equations, law of sines or cosines, depending on what information we have. So in terms of angles, we'll call that little q, that'll be little p, and that'll be little r. So those are the internal angles. Now we've got our measurements of our p's, but most of those are external. When we think of those, that's 50 degrees from the horizontal, right? We measured that basically from the thing. If it's 50 degrees there, remember our geometry when we have two parallel lines. So if it's 50 degrees there, then this angle will be 50 degrees here. Okay, that one was measured at 25. And then some unknown things we need to get out of the way here. Let's see. We'll call that alpha. And that's the angle we're going to be interested in solving for. And then when we look at this angle here in terms of Q, basically, well, again, in terms of parallel lines, I got two parallel lines. If this is 25 here, this piece will be 25. And then I define this as an alpha here, so I'll have that portion as alpha there. So again, what I'm trying to do is I need to capture what's going on the inside. I need the internal angles to be able to use my equations there. So let's just think of what we've got. So R I can find right off the bat, because I've got a straight line of 180 degrees. I subtract 50 from this side and 25 from that side. I end up with 105. Little p is going to be basically this angle here. So it's going to be 50 minus this unknown alpha that I need to solve for. And then when I think of q, I can sum up those two pieces there. OK, so again, thinking of information that I have here in terms of knowns, what do I have in terms of forces? How many knowns? 2. I got P and Q. How many angles do I know? 1. OK, so which equation makes the most sense? Law of cosines. So let's consider plugging in our law of cosines. What we're interested in is R. And the nice thing about cosines, when we think about it, R is the piece I want, and I need the angle directly across from that. As we can see from here, R is what I want, and the one angle I know happens to be the one directly across from it. So we can go ahead and plug that in. We'll put up the terms here. Did I forget the 2 in that? No, I got it. So I just simply go ahead and plug those pieces in, and what I find then does that make sense? Is it reasonable? Seems a little big, doesn't it? What do I need to do? Square it, yeah. Remember, it's r squared. I bring that up because people always forget that little piece there. So in terms of carrying it out, basically, I spread it out a number of terms there. But in terms of reporting it, I'm going to keep it down to 3 or 4 digits there. And then finally, what I want to do is find this angle here. So now that I've got all of my forces there, law of sines make a whole lot of sense, because what I'm looking for now is an unknown angle. And we'll go ahead and stick that here. So again, when I'm plugging it into the law of sines there, note a couple things there that I put in my R, but I put in my R with all those extra digits. Again, an interior calculation. I'm not reporting that, I'm putting it into an equation, so I need those extra digits there. I found the sine of that and what I found then is the P, but I'm not really interested in the P. What I'm interested in is reporting the angle of that R based upon that horizontal, and I managed to erase the thing I'm interested in, but we go back, what we want is alpha. So we just simply go back to that relationship that we set up there earlier where we tried to find P based upon alpha, switch it around, look for the alpha. Okay, any questions on that one before we dive into problem 2.8? Okay, so I guess I'll hold it up here. Okay, we've got a couple of ropes here basically pulling on a car. And a couple of key things we need to think about is what information we have. Do we know the direction of the resultant? Go ahead and read the problem if you want there. So we know AB is 2.2 kilonewtons. We know the angle of alpha is now 25. We've got the other one already defined as 30. And then it says, knowing the resultant of the two forces applied at A is directed along the axis of the automobile. So basically, they've got a couple of forces acting on that. What they want to do is have those forces such that they're pulling it in a straight line. So the resultant force that the car we want to see basically is pulling the car in a straight line along the axis of the car there. So basically we know that direction. Okay, so we'll just talk about what we know. We pull up all of our forces here. So we've got the force in AB and AC, and then there's some sort of resultant there. And we just need to think about what we've got. Now, AB, we've been given 2.2. AC and R, no idea. So those are unknowns. And do we know angles? And I'm putting up angles with respect to x. So basically, do we know some sort of an angle with that? Our AB is a known at 30. Our AC is a minus 25, so it's on the other side there. And then we know our resultant is going to be along the line of the axis there. So basically, we've got 3 known angles and 1 unknown magnitude. Now, this particular problem asks us to solve basically the tension in AC, and then part B looking at the resultant magnitude, basically, of the two forces using the trig approach. So the trig approach means we're going to be using our law of sines and cosines. So first thing we're going to do is draw the triangle. Look at the angles and see what we have. Okay, so our first one, our AB, is going to be at 30 degrees there with the horizontal. AC is an unknown. But the nice thing about that is that I know that particular angle. And then finally, my resultant, again, I know that angle too, because it's going to be along the axis of the car there, so it's described like so. And I have a little r there, and I've actually got my two internal angles already defined there, because nicely the resultant force is going to be along the horizontal there. Now r, we can even calculate that one when we think about it, because this will be we can look at it that way, or what's the sum of internal angles of a triangle? 180, okay? So we can find r by taking a straight line, and basically what we see is we subtract those two internal angles, which is basically what that is doing there. So what we find, basically, we can define all three angles with this particular problem because it's rather simple. And I'm using the wrong color here. Now, since I know all of the angles there, basically what I can do is basically use my law of sines. I don't even have to worry about going to law of cosines. So if I set up my sines equations, I can basically set them all up in the one equation there, noting that this one I've already, oops, not 2.5, 2.2. So my only two unknowns, and all I need to do is just set up the equations where I multiply sine of 30 for that one or sine of 125 for that one. And one thing I'll note here too, one of the things when we start reporting, we're talking about vectors. So when we talk about forces, we're going to need to start thinking about reporting them not only in terms of magnitudes, but in terms of directions. So a lot of these they're already defined, but just get used to the fact that when we start thinking about forces, when we describe a force, it's always going to be a combination of a magnitude and some sort of a direction. Now, oh, sorry.
Can you determine the angle that we're looking at? So if you have AB and over sine 25, just the opposite side of the angle, is that what you pick?
Yes, yes. Remember, the way a law of sines works is it's always a over little a. So this one over that one. Does that make sense? Yeah, just get comfortable with that. Now, we'll be seeing this when we get into friction and some of the three force equations and stuff like that. It's a very nice, quick way of getting there. Any other questions? Okay, so where we're going to go next now is this works really nice if I have two forces, right? If I have three forces, can I do this? Actually, you can. What you can do is if you've got three forces, okay, so you got three forces, like so. What you can do is take two of them, create a resultant, right? Then take that resultant, add that to the third force, and you get something like that. Now, do you want to do that? What if you have 4 or 5 forces? That's going to be a bit much. So what we're going to do is looking at a way that we're going to do that in terms of expressing it in terms of rectangular coordinates. And this is the way a lot of our course will go, and especially if we're in 3 dimensions, it's about the only way to go. And this will be your section 2.2, which I'm sure most of you have already read. Another way this is expressed is called Cartesian coordinate system. And the key thing here is we're going to be dealing with perpendicular axes. And a couple of important things that come out of this and why we like this. The x and the y coordinates are independent. So if I change something in the y, it doesn't necessarily affect anything in the x. It doesn't affect anything in the x. If I change it in the x, it doesn't affect anything in the y. And what we're going to do is we're going to describe our force now in terms of components along those axes. So I'll have an fx component, and I'll have an fy component. Now, what we're going to do is describe this in terms of what we call unit vectors. We're going to have unit vectors And remember, I told you there's going to be all sorts of weird little symbols for a vector, underline, arrow over the top. And then the one your author likes for unit vectors is hats, little hats like this, little triangular hats. And what we're going to use those for is establishing directions. And the reason why is because it's the unit vector, it's a unitless value of 1. And the nice thing about 1 is when you multiply a number times 1, what do you get? You get the number. So it's a magnitude 1. It doesn't have any units. And basically, the only reason it exists is to establish directions. So our I hat is going to be in the positive x direction there. Actually, I should put that down. The way they're established is if you establish a positive x direction and a positive y direction, then the unit vector I hat will be pointing in the positive x direction, and the unit vector j hat will be pointing in the positive y direction there. So that means I have this vector here. I can express that vector now in terms of two vectors. So again, this looks like a parallelogram when we look at it, right? We've got it just happens to be a rectangular parallelogram. So I can express it in terms of these vectors here, or I can express it in terms of these unit vectors. Like so. And the key thing is then these pieces here are scalars. So I can talk about those. They're not vectors. This combination is a vector, but it's a scalar times that directional information we have there. And it'll get more complicated when we get into 3 dimensions because we'll add then our z direction there. And the main reason we do this is it's basically going to be a bookkeeping tool. What we're going to be able to do is find all the things with I hats and all the things with j hats, and then we're going to combine them. So that's where we're going with this. So again, getting to the point now where we're dealing with multiple forces. What we're going to do is break all of our forces into components and then add up those components. We're going to add up all the I hats, all the j hats. So it'll be a multiple step process. Okay, so what we're going to do is take our forces, I keep blocking you here, and we're going to break them into and I make sure that it's a common xy system. So we don't want to rotate it for this force and do it this way for that force. We've got to pick a common system. We're going to break it into those components, those x and y components, fx times I hat, fy times j hat. And the nice thing about that So what we're going to do is then take all of those things that are related to the I hats, we're going to add them together, and all the things with the j hat, we're going to add them together. Now the key thing here, though, is we've got to pay attention to signs. So again, positive x is going that way. If the force is pointing the other direction, that's negative then. So we've got to pay attention to that. And this is where our bookkeeping, this is where we want the I hats and the j hats. When we break it up into those things, then we can easily see the pieces that we need to add up. And then finally, what we're interested in is finding this resultant. Now, depending on what we've been asked to solve for it, we might need to find it in terms of the magnitude of direction. We might be able to leave it in terms of just x and y components. You have to look at the particular problem. Okay, so first of all, we'll just talk about how to decompose that force. It's going to be a couple of different ways of looking at it. My colors. And I don't know why I did that, but that's, instead of an F, I decided to go with a P, so sorry about that. Let me. Okay, so via magnitude and angle, it's pretty straightforward. If we have it measured, or we have a coordinate system that we've established, and again, this is a system we can set up ourselves. It doesn't necessarily have to be horizontal and vertical. What we'll find is that we can rotate it to something that's maybe easy to measure if we might have measurements in terms of certain directions and stuff like that. So the coordinate system is not fixed as a horizontal and vertical. We're going to be able to choose that. But once we choose it, especially when we get to this point here and we've got multiple forces, we've got to stick with the same one. Okay, so magnitude and angle implies then I've got a magnitude and I've got some measured angle that I can deal with. So I can then calculate those with a known angle that I've measured somewhere, and I've got a known magnitude. I can simply break it up into those x and y components there. I feature measuring the angle from y because when we get into 3 dimensions, we're not going to be using sines much. It'll be mostly cosines. So everything will be measured basically from those axes there. But just realize you have the power. You can choose one or the other, not a problem. And then noting then we can calculate that angle, or we express that angle, and noting that the angle is, this particular tan is just simply a function of that magnitude over that magnitude. Another way we'll see is given a couple of points on a line. So what that will look like So I don't have an angle, but I've been given a location. So I have a location there. Say, for example, you could think of it in terms of a cable on a guide tower. You might know the point there somewhere on the tower where this is located, and then you've got an anchor point down here. So a lot of times you'll be given that information in terms of just a couple of points there. But again, all we're going to do is simply construct our algebraic, our geometric sines and cosines, but using a couple of points now instead of. And let's see, I guess we'll call that point O, just so we have that. So what we're going to do, and then, of course, the key thing is there's going to be a force going along that line. So again, like, think of it in terms of a tension cable or something on a guide tower there. We got those 2 points. We know there's some sort of a magnitude in that tension, but I need to establish now direction, and the way I'm going to establish it is using the 2 points. So the first thing I want to do is just simply establish the length of that cable there, between the two there. 2 ways of expressing it, remember, using the absolute value signs or the little arrow over the head. Or actually, no, I don't want to do that. That comes later. And I just simply, because it's rectangular there, and we're doing it with a perpendicular axis system, I can use the Pythagorean theorem there, and the length is going to be equal to phi from O to A. But that's not what I'm interested in. What I'm interested in is establishing the components and note that my px component will be simply the fact that if I know this distance is 4, then the sine, or the cosine there, or no, that'll be the sine, no, the cosine, will be simply 4 over that magnitude, right? So are we comfortable with that? I haven't lost anybody there? So remember, sines and cosines are just simply ratios. Ratios of these perpendicular lengths over the total length, right? Been a while, I'm sure, since we've done some of that. And then py is the same thing. It'll be that height now, which is 3. And then if I need to calculate the angle, and again, tan is also just simply a ratio, set of ratios there, except that's now not the diagonal there, it's including the 2 perpendicular lengths there. But where we're going with that then is to be able to express each of the forces now in terms of a component of x and a component of y. 2 different approaches depending on what information we've been given, but pretty straightforward to go through. Okay, our next step then is just simply we're going to be adding those components. Okay, so I've got a set of forces that are all intersecting. Now, the key thing here to note, too, is what we're talking about. When we're talking about forces and adding them together, the key thing is, first of all, they all have to intersect at a point. If we got forces off in different directions and stuff like that, that'll be chapter 3. We'll get into that. So right now, we're talking about forces. The first thing we need to look at before we say, geez, I'm going to add all those together, do they all intersect at a point? are they concurrent? And that'll be the cool word that you'll get to impress your English friends with, English major friends with and stuff. Concurrent is going to be the key thing here. The forces all have to intersect at a single point there. So what we're going to do is then have to go through oops, get some signs in here correctly. And again, key thing is paying attention to those signs. So when we think about P, when I think about those two components there, well, I look there and I notice that both the x component and the y component will be positive because they're in the positive quadrant there. When I look at Q, my x component should be positive, but my y component now is heading down. So we're going to put that sign in. The key thing is to make sure that we keep track of all those signs. And then S basically is in the negative quadrant, negative quadrant. So basically both of those pieces are going to be negative. Okay, R is going to be a combination of the same sort of thing, but what we're going to do is find that I can solve for Rx like so. So the nice thing is, once I've got it to broken these into x and y components, then to get my R, which I'm interested in, note that the x component for R, for my resultant, is simply going to be a summation of those things. But I have to pay attention to signs there. So I'm going to be a positive Q, but a negative x. We'll end up with whatever we end up with. If it comes up negative, that means it'll be pointing in that direction. If it comes out positive, it'll be pointing in the positive direction. And the same thing with the y components there. And again, depending on the magnitudes, things will go off into different directions there. Now, that's one way of expressing our resultant, but oftentimes we're going to be interested in finding out, okay, what do I have to design my bracket to hold? So in terms of calculating the magnitude, I just simply use Pythagorean theorem in reverse there, basically, and solve for my R. Once I solve for my x component and my y component of R, okay, and the other key thing is then calculating that angle. Be careful when you're looking at problems, and EIT exams will do this sort of thing. Be careful what angle you're reporting. Okay, if you calculate the angle as rise over run and that sort of thing, then it'll be with respect to the x-axis, positive or negative, depending on how you're measuring it there. So be careful. They might say, geez, give me the angle with respect to the horizontal or the vertical axis and that sort of thing. So just read the problem. You've got the tools to do it, but just don't go into it in a rote mode and charge it along there. Okay, we'll do a problem 230, the telephone pole, which is a real type problem that your SMUD folks are doing all the time. Okay, so you wonder why, you know, on telephone poles, why they put those cables there. They're not basically there to trip you up and that sort of thing. The idea is that, okay, I've got a telephone pole and I've got a horizontal force. Maybe I've got a line running over to a building and that sort of thing. And I don't want to have a whole lot of moment here down at the bottom. I may not have it deep enough or something like that. It might cause some problems. So they tie them off with forces. So they're very, when you look around at telephone poles and stuff like that, very nice, easy statics problems. But the key thing we need to do is that we've got this cable there, BD, that we're going to tighten up to some sort of value. And what we're saying is okay, what value I need there is I need a 720 Newton component that's perpendicular to the pole. So my pole is like that. And what we're saying is that we've got basically a 720 Newton pole on that, and I've got this cable. The way I'm going to rectify that and keep that from having the pole topple over there is that I'm going to have this cable here, of which I want my 750, good job. I want the component of that cable now to be 720. So just, again, thinking of a couple things in terms of reasonableness, will the cable be greater than 720? Yeah, it's the resultant there, so that's that big thing there. I only want that little piece there, and it's probably a relatively flat angle there. So, and I suggest folks to, you know, and when you're looking at exams and that sort of thing, read the problem a couple of times. Remember the old adage of, what is it, measure twice and cut once? If you're into costume making and that sort of thing. With problems, read them twice, because a lot of times you might miss something. You're in a hurry, you know your methods and everything, but you need to think about it in terms of that. So what we want to do is think about our force now in terms of components. And all of my cool colors are down here. So it's always good to establish a coordinate system. Okay, so it's usually, that's why, again, we work with quadrille paper and stuff. So we want to draw the problem out, just get some sense of how things are working there. So we've got this force, and we basically want the px to be equal to the 720. Now, a couple things we need to get out of the way is we've got an unknown angle here that we have to deal with. So first thing we need to think about is, okay, which one is this? Do we have a defined angle, or do we have a defined points? Got a couple of points there. We got a point up there at the top there, measured at 7 meters high, and then we got the anchor for that particular cable at 2.4 over. So in terms of thinking that, we got to work out our angles here. Now, you can either do it in terms of ratios or you can do it in terms of angles. I don't particularly care. Whatever you're comfortable with, go ahead and do it the way you're comfortable with. this particular example, I'll just do it in terms of the angle there. I could actually scan this and post both solutions to you. But the key thing is, okay, now what we have is an inability to write the right number. We know that px has to be the 720. That's going to be, we've got that pullover there. But remember, that's equal to p times sine of that angle there. So I can set up and solve for p right off the bat by setting and what we find then is the cable, as we suspected, was going to be a lot bigger than basically what that horizontal force is, the horizontal force I need. And then, again, when you're designing these, you want to know what the Py is, because you've got to make sure your column doesn't collapse or your pole doesn't collapse. But that's just simply going to be a straightforward simply taking the cosine of that particular angle there. So that's why we trip over those cables all the time, because they're really quite taut when we think about it. I needed to get a 720 in terms of a horizontal, and I had to crank it up to 2,220 just to get that component based upon the angle of where I could put that cable in. Okay, we'll look at the next problem. That's going to be the sort of thing that why we want to do this in terms of Cartesian coordinates, because it's a bunch of forces now that we're going to have to break up into pieces here. Okay, so this is a situation, again, where we're going to go Cartesian. We don't want to necessarily do two applications of the trig rule and that sort of thing, force triangles. So some of the things we're going to have to do is, again, this has been given to us as a set of points. In this particular example, instead of calculating an angle, I'm going to use the approach of ratios. And when we get into multiple things like this, it's usually best to do it as a sort of set it up as a table. So a couple of things. First of all, again, we've been given these distances, so the first thing we're going to have to do is find the chord lengths there, that diagonal length there. Oh, I guess I don't have. This is A. This is B. And this is C. And then our origin, of course, is O. And that chord length is just simply going to be 1/16. And note your author likes to play with numbers that come out to real nice even numbers. Be aware, when I give exams, I don't do that. Real life, you're not going to deal with real nice numbers like this. There's always going to be something you're going to have to think about in terms of truncating. Okay, so now I can establish those ratios because I've got my diagonal lengths established. I think we'll try to keep, got this. I'm going to use this portion of the board here. Everybody got it before I erase it?
This one?
Yeah.
Not yet.
Okay. And then, like I say, what we're going to do is want to set up a table. It's usually a little easier to keep track of things in terms of allowing the table to be set up. Just about there?
Yep.
I'll start erasing from the top. I'll erase really slow. Can talk even slower. Okay, so we'll have 5 columns. And we're going to have each of our forces. So we'll start off with our first one there, OA of 29. The ratio, or if you want to look at it in terms of sine or cosine, it's simply going to be that. And that comes out as a positive in the x direction. And since it's all in the positive quadrant there, the Fy component will also be positive. Okay, our 50-pound force. Now that ratio is going to be a little different there because now it's coming back 28. So my 28 I'm measuring now in the negative x direction. So I need to make sure I put in that minus sign there over the diagonal length there. And what we'll find is its component in the x direction will be a minus 14. And then the y direction will be also positive. And it makes sense. Think about, again, that's why we draw things out. Well, the component in this direction will be up. This component in this direction will be negative. And then our final piece there, the 51-pound load. In the x direction, again, it's still positive, so end up with a positive 24. But it's acting down, so our negative direction will be a minus 90 over the 102, like so. So its y component will be negative. And once I've established this table, all I need to do is just sum up my x components, and I sum up my y components. And what I solve for now is the components of the resultant. It's going to be a 31 in the positive x direction, and it's going to be 23 in the positive y direction. So all of those guys sum up basically to a force off here into the positive quadrant. So one way we can report the resultant may be in terms of I and J. So again, look at the question on the exam and that sort of thing. Does it say solve it for me in terms of I and J? Or is it interested in finding that magnitude, which is just simply going to be an application of the Pythagorean theorem of those two pieces there. And then in terms of finding the angle, it'll be a positive 36.6 with respect to the x-axis there. So when we think about what that looks like, when we sum up all of those forces, this is basically what our resultant looks like. Okay, and we're right up to the end of class there. Any questions before we take off? Huh? Oh, yes, yes. Actually, we should be doing that at the beginning of class, but if you got the homework, bring it up here and leave it off here. There is, folks, there's a homework 2 on the CT website. There's also a homework 2 hand-in. So you'll download that, work on it, and you'll turn that in at the beginning of class on Tuesday then.